For this screencast, we're going to get the pH of a weak acid. Now, for a weak acid, it's different than a strong acid. For a strong acid, you can assume a 100% reaction. For a weak acid, and bases, but for a weak acid, you cannot assume a 100% reaction. So you cannot assume stoich. You're going to have to use a K equals products over reactants type math, and notice the K value we have here. We don't know to what extent the acid, in this case acetic acid, will ionize to the two products. And according to the Arrhenius definition, it ionizes to H+, it produces H+, that's what an acid does, that's what a Arrhenius acid does. And then you get the anion, the everything else. It's a -1 charge because it is charged balanced. It starts out as neutral. The reaction starts as neutral. It's aqueous. We know it's aqueous because of the molarity. That tells me it's dissolved. The H comes off. That's what an Arrhenius acid does, and it produces H+, and then the anion stays together. It doesn't get ripped apart atom by atom. It gets ripped apart, one hydrogen atom coming off as a hydrogen ion with a +1 charge, and then the anion stays together. And these dissociate to be aqueous as well. You could also think about acids reacting with water, but it's a bit simpler to focus on just the dissociation of it. So we're going to set up an ice chart, because what we're going to end up with is K equals products over reactants, which is H+ over C2H3O2 minus 1, and the reactant on the bottom, the acetic acid, right here. Now, this equation, K equals products over reactants, demands equilibrium concentrations. What we have here with a 0.3 is the initial concentrations. And so we need to set up an ice chart so we can convert initial conditions. It's going to change into the equilibrium conditions. So initially I have 0.83 molar acetic acid. Before the reaction starts, I have no products, no H pluses and no C2H3O2. In terms of the simplest form, technically there is some H plus in there just from the water itself, 1 × 10⁻⁷ and that would have an effect on it, but for simplicity's sake we're going to assume that 1 × 10⁻⁷ is very close to 0, and write down the 0. During the change, I'm going to lose reactant, which means I'm going to lose negative sign, some reactant. I don't know how much it is, so I put the variable x there. I'm going to gain products, so that gives me plus signs. I still don't know how much I'm going to gain, so I get x's. Now the x's is the same. The x is the same for all three, as opposed to x, y, z, or a, b, c, 3 different variables. I know it's the same because when I lose 1 acetic acid, I'm going to produce 1 H+, and I know I'm going to produce 1 acetate anion. I know it's 1 to 1 to 1 thanks to stoich. It's never, it could be a 1 to 2, a 1 to 3. It's always going to be based off the balance coefficients, but it's not going to be any other random number. For every 1 dissociation, I'm going to produce 1 H+ and 1 anion. Now I have a singular arrow drawn here, and to be correct, it's a double arrow to show that it's going to be a reversible reaction, as opposed to a 100% stoich reaction. I know it's going to be some type of ratio of product to reactants. So I initially start with the 8,3. I'm going to lose X amount, so I'll end up with 0.83 minus X, X, and X. And it's this equation, this bottom row, that gets put into this equation here. At equilibrium, this is how much I'm going to have. And so we're going to plug those numbers into it. K equals X times X, substituting the X for the H plus, substituting the X for the C2H3O2 minus, divided by the acetic acid, which will be 0.83 minus X. That equals the K value, which is 1.8 times 10 to the negative fifth. So from here you can solve for X. It's going to involve a quadratic because the numerator is X squared and the denominator is minus X. Now for our class, for simplicity's sake, we're going to take advantage of what chemists call the 5% rule. If K is really small, which K is times 10 to the negative fifth, that means 1 in every 10,000 reactants will react, so that's considered a small value. X is going to be small because only 1 in about 10,000 is going to react. I guess 1.8 in every 2,000, 10,000 will react. So that's a very small number. So what that means is that X will be small. That means 0.83 minus a very small number is still approximately 0.83. It's not an algebra move, it is an estimation to save some time for algebra. In this case, we're not foiling the denominator, which will cost time. We would have to do the quadratic, which will take time. If we had x to the third or x to the fourth value, then algebra becomes even harder to do and just about impossible to do without estimating. So this saves some time and effort, and for the purpose of what we're doing here, we can go ahead and say that X is so small that it's not going to change the denominator away from the 0.83. And you have to validate that. So how small is too small? How big is too big? At the very end, you would show that the X was less than 5%. 5% is relatively arbitrary, but is still a very small number. And so we can do that to show off the fact at the very end that 0.83 minus X is still approximately 0.83. So now the algebra becomes a lot simpler. Multiply both sides by 0.83 and you get $14.94. Take the square root of both sides to solve for X and you get 0.003865. Now X is not our answer. So part of the skill is, congratulations, you solved for X. Now you have to answer the question, find the pH. So how do we do that? pH equals, P stands for negative log, also power, but mathematically it stands for negative log of the H concentration. So what is the H concentration? Well, according to our ice chart, H at equilibrium is X, which means this value here, X, equals our H plus. And so I can plug that value into it, take the log negative, and you end up with the correct answer. Now, if your calculator will say 2.41 as opposed to 2.42, I'm trying to show off the fact that the last sig fig you can be off a little bit depending on where you rounded. Perhaps you rounded this to 2 sig figs right away and did 1.5 or 3.9. It's okay to be off by a little bit, representing the answer. That's what we have. And so that's how to get the pH of a weak acid solution. Now, if you want to go back and validate the estimation, you certainly can. X divided by 0.83, what percentage is that? It won't be too hard to do. So 0.003865 divided by 0.83. Convert that to a percentage, and you get 0.46%. And so that's a very small number. And so in certain levels, you'd have to actually verify that the estimation was okay. You can also subtract here and do 0.83 minus x, and now actually substitute the x value in. You get 0.83 minus 0.003865, and you get 0.826135. Rounding that to proper sig figs, you keep the number of decimal places 2, so that rounds up to 0.83, and that's actually the same as what we estimated it to be. And so we saved ourselves some time in terms of algebra. It's not just a time saver, it's also a saver in terms of not being able to solve for something to the cube root to the fourth root. But we digress. The question asked us to find the pH, and that's what we did. We can't just take the 0.83 and assume that is equal to the H plus concentration. You can do that for strong acids, but you cannot do it for weak acids. For weak acids, you have to go through the ICE chart, come up with your K equals products over reactants expression, solve for X, and allow X to, or realize that X equals to the H plus concentration. Take the negative log of that, and you get your answer. A few more problems to do. Enjoy.